talk will be about existence and uniqueness, solution to the Lifshitz-Slyozov system with monomers space.
Okay, thank you, organizers, to have invited me to this kinetic workshop. Okay, here I will talk you about existence and uniqueness solution to a complex Lifshitz-Slyozov system. This work is done with Thierry Goudon and Frédéric Lagoutière. Okay, before talking about this, let me just say a few words about the standard Lifshitz-Slyozov model. This model describes the evolution of the population of monomer, the evolution of a population of microparticle or polymer immersed in a bath of monomer. In this solution, we have appearance of interaction phenomena between macroparticles characterized by their size repartition function and the monomer characterized by their concentration. These interactions provoke the growth of large particles at the expense of smaller one, what is known about Oswald ripening. Okay. The evolution dynamic is governed by the following partial differential equation. The first equation is an advection one for the size repartition of macroparticle. The second equation is an preservation mass one with Ct represent the mass of monomer, and here we have the mass of macroparticle with the following initial data. Exactly, in the Lifshitz-Slyozov model, standard model, they use the kinetic coefficient xc equals c and b equal 1. Okay. The evolution of this system is governed by the velocity v that depend on the kinetic coefficient a and b. These kinetic coefficients represent the rate at which monomers are added to or removed from macroparticle of size c. Of course, the choice of the kinetic coefficient a and b depend on the precipitation dissolution mechanism. This system, without its apparent simplicity, is very intriguing in mathematical analysis. And we have some conjecture given by Lifshitz and Slyozov, and the main conjecture is that the asymptotic behavior of the size repartition function is universal. That is I don't know what to say, but many theoretical and numerical results are in contradictory with these conjecture. And for example, we can quote the study done by Nyatamer and Pego, and in their work on the initial value for the problem of the Lifshitz-Slyozov model, and they show that the asymptotic behavior, we have not an universal asymptotic behavior for the size repartition function. And numerically, we have some result that enforce that mathematician position, and this result is done by Carrillo and Goudon. And numerically, they show that we can have many behavior for the size repartition of macroparticle. And as an answer to this mathematician position, the physicist has argued that in order to have this conjecture, we can take into account encounters between particles. As here, when we have our system, we can take into account encounters between particles in this operator, which is a Smoluchowski operator. with, of course, the okay. And other results are available with this same system, taking into account encounters between particles done by Herman, Nyatamba, and Velasquez, and they were able to show that we can have solution for the large asymptotic behavior, but they are not able to say something about the uniqueness of these solutions. Numerically, we have a very interesting result when we look with the system, with encounters and without encounters, and this result is done with Thierry Goudon and Frédéric Lagoutière. Here I am not talking about the debates between mathematicians and physicists, nor in the asymptotic behavior. I'm just interested in the way to extend the Lifshitz-Slyozov model when we take into account the position of macroparticle and monomer, and when we assume that the monomer follow a diffusion equation. Okay, and I will follow this outline. In first step, I will state our new model, what we call complex Lifshitz-Slyozov model. In the second part, we will say some tools about this model by giving some result on parabolic equation and some result on advection 1. In the step 3, we will say something about the existence and uniqueness solution of our new system by stating our general theorem and by splitting the way of the proof to deal in first step with bounded data and in second step with general data. Numerically, we are interested to the influence of the monomer diffusion to the evolution of the size repartition function of macroparticle. And I will give what we do numerically and some perspective on this work. Okay. For the first step, here is our complex model. Here, f is the size repartition function that depend on time t, on position x, and of course of the size xi. And the first equation is an advection 1. For the second equation, we have a diffusion equation for the monomer concentration. We say that x belongs to omega, that is include on x belong to omega, that is include on Rn, which is a bounded, which we take that omega is a bounded and smooth domain. We endow our system with this following homogeneous Neumann boundary condition, where nu x is the outward unit normal vector and x, okay, on omega. We complete this system with the initial conditions on a time t equals 0 and a time, okay, and here. Okay, it is natural to do this following hypothesis on C init and F init, which represent the fact that F init has his first and 0 order momentum bounded. Okay, by using the conservation equation for the size repartition function, we can rewrite by integration the equation for the concentration of monomer as this following familiar fashion. Of course, our system satisfies the total mass preservation. Naturally, we do the following hypothesis for our kinetic coefficient. We take B equal to 1, A satisfy the following regularity, and we see that our hypothesis take into account that the hypothesis done by Lifshitz and Slyozov. Okay, for the resolution, I want to say some word about the parabolic equation. Let given A and B, two non-negative functions belonging to this space, and T fixed, we have existence and uniqueness of solution to this parabolic equation when the initial data is chosen in L2 of omega. Furthermore, we have, when the initial data is uniformly bounded, we have the maximal principle that is satisfied here, and we have energy estimate satisfied by C, with, of course, C, capital C, T, function of capital C naught, T, omega, and the L2 norm C init. As a sketch of this proof, it is very standard. We define the bilinear form here, and we verify that this bilinear form is well defined in H1 times H1 of omega. We prove that this bilinear form satisfies the following continuity estimate, and it is coercitive. Then we can apply a light version of Lax-Milgram theorem for evolution equation to give the proof of this proposition. For the maximum principle, we obtain this just by Stampasian argument. Okay. Let me say something about the advection equation. For this following advection equation, here we require that our kinetic coefficient A, AXC, is more smooth than what we state in our hypothesis 2.1. We suppose here, say, in C1, okay, and there is no matter, this assumption will be removed after when we deal with general data, and we need this more regularity on XT in order to apply the characteristic curves. Okay. Okay, when we introduce the characteristic curve associated to C and parameterize it by X as follow, we can then express the size repartition function of macroparticle as follow, when of course J is the Jacobian of the change of variable and his expression is here given by this. Of course, we can say something about the Jacobian. We see that the Jacobian is bounded above and below when S is lower than T. Okay. The expression asterisk for F allow us to give the following proposition for the advection equation. Let the kinetic coefficient A smooth and F solution of the given asterisk equation. Then we have the solution F is continuous and belong, and his zero order and first order momentum is bounded, and F satisfies the following estimate. For the sketch of this proof, we use just the relation asterisk, and we do some integration on it. Okay, and we use the fact that the Jacobian of the change of variable is bounded above and below. That complete this proof. Okay. Now we have some result on advection and on parabolic equation. Now we can state our main theorem on our system. Let's suppose our hypothesis 2.1 fulfilled. Then there exists an unique solution, unique weak solution CF of the space diffusion system with, for T finite, C and F fulfill the following regularity. Okay. And for the proof, we use the Schauder fixed point theorem, and we do this by following the two following steps. In first step, we prove the theorem for bounded data. That's why previously I suppose A more regular. In second step, we extend our result in the result obtained in the first step for general initial data. Okay. For the first step, we assume here that we have bounded data. Okay. We suppose that F init belong to L infinity of omega times 0 infinity, and we suppose also that our assumption xc is more regular than what is stated in our assumption 2.1. Okay. And the proof is done as follows. We have defined a mapping F, then for C tilde we associate C tilde, we associate C with C satisfying our diffusion equation, partial T C minus Laplacian C plus AXC equal B with our boundary condition, and we have our objective is to prove that there exists a fixed point for this mapping. Okay, for that we set this space 0t times omega for fixed t. We denote C naught and capital KT as follow. We introduce this space CT and we define our mapping in this space. Okay, with C satisfying our diffusion equation, where A Tx is defined as follow and B is defined as follow, and the function f satisfy the advection one, this following advection one with tilde c. Okay, and then thanks to the proposition on the advection equation, we deduce that we have this estimate on A and B. That's give that our mapping is well defined, and the solution C belong to this following space. we use the maximal principle and have that C is bounded below, above and below, so that we have this following inclusion. For the compactness property of this set in L2, we use the fact that C is bounded in L2 and the time derivative is also bounded in this space. And the fact that H1 embeds compactly in L2 allow to use the Aubin-Simon lemma and we have the compactness property. Okay. For the continuity of our mapping in L2 norm, we have to prove that if this sequence converge toward tilde C, then we have Cn converge towards C. To this end, we define Fn and F as solution to the following system. And thanks to the characteristic curve, we have the following estimate on Bn minus B in L2 norm and An minus A in L2 norm of dt. And this following estimate is obtained by the fact that we have result on the difference on two characteristics, theta 1 minus theta 2. Okay. By energy estimate and Grunwald lemma, we obtain an L2 estimate on Cn minus C as follow. Then we can pass to the limit and show that Cn converge towards C in L2, which complete the proof of the continuity. And by Schauder theorem, we have existence of solution. Okay. For the uniqueness of the solution, here we use the same technique that we done in the continuity part when we prove the continuity of our mapping. We assume here that we have two solutions, C1 if 1 and C2 if 2, and and we start for the same initial data. We suppose that we have the same initial data. We prove the following estimate on C1 minus C2 in L2 norm. And then we apply Grunwald lemma to see that C1 is equal to C2. That's to prove our uniqueness result. Okay. Here we have proved the existence and uniqueness solution for bounded data. But we know that bounded data is physically questionable, and we have used more assumption, more regularity on the kinetic coefficient AXE. That's why we require here F init belonging to this space, and we have the 0 and first order moment term is bounded. And to prove our theorem in this more general initial data, we do some regularization by considering a sequence F init n, a bounded sequence that converge toward our initial data and satisfying the following assumption. Okay. As an bounded sequence is possible, we can use the fact that F init n is F init okay. Okay, we can choose this following example with, of course, Cn can converge to infinity when n converge to infinity. We can associate to f init n, our sequence, the following system, solution of the following system. Okay, we deduce as previously that Cn is bounded in this space and the time derivative is also bounded in this space, and then we can apply the Simon lemma and have the compactness result. Okay, then we have proved Cn converge towards C strongly in L2. Also, we show that Cn converge towards C in this space weakly, and by using de la Vallée-Poussin lemma, we show that we have the following estimation with, of course, phi is non-negative, convex, and coercive function satisfying the following initial bound. Of course, here we use the fact that our Jacobian J is bounded above and below. Okay. So, the Dunford-Pettis lemma imply that when we use the equation on advection 1, the Dunford-Pettis lemma imply that Fn is relatively compact in L1 to this product space. That lead we have the weak convergence of Fn toward F. We also prove that An converge weakly toward A, Bn converge weakly toward B, and by the Dunford-Pettis and Egorov theorem, we can pass to the limit at the nonlinearity. Cn Fn converge weakly toward Cf in L1, and An times Cn converge weakly toward AC in L1 0t times omega. To complete the existent solution for general data, we show that the partial derivative of Fn is bounded in this space. Then we have Fn is compact in C0 of this space. Finally, we can let n goes to infinity in the regularized system and obtain the existent solution Cf. For the uniqueness solution for general data, we begin by assuming that we have two solutions, C1 if1 and C2 f2, with the same initial data. Okay. Instead of the usual L2 norm, that we use the L2 norm but it don't work, instead of the usual L2 norm, we derive an L1 estimate for C, and we have the following estimation for the L1 norm of C1 minus C2. How? 5 minutes. Okay. Okay. Okay, we have the following estimate. Okay. In order to bound this two last term, B1 minus B and A2 minus A1, we use just the same reasoning done by Lorenzo in his article when he deal with the weak solution to the Lifshitz-Slyozov system. What prove our existence and uniqueness result. Okay. Numerically, we have done something to say just the influence of the diffusion of monomer in the size repartition function of the macroparticle, and we obtained some result on it by using the following algorithm. For the advection equation, we use Rezanov scheme, and for the diffusion equation, we use the standard discretization as follow, and we write all things in matrix form that allow us with this initial condition on C init, we write it C0, and F init F0, we have the following result, numerical result. Here we have the initial size repartition function of macroparticle. In this axis we have the position of particle. Here we have the size of particle, and at time t equal to 20 we have this following behavior of the size repartition function. Okay. For the concentration of monomer, we choose this initial value. We suppose that our monomer is locally dense, and at time t equal to 20 we have the following behavior of C, and of course we have the total mass preservation, which we can show in this picture. Okay. There are many perspectives here, and I thank you for your attention.
Thank you very much. Are there some questions? Well, it concerns the second point, so the long-term asymptotic behavior from the numerics or from anything else. What do you conjecture? What would be the guess for?
Okay. Here we don't look the long-term asymptotic behavior because it is very difficult numerically to look at it, because we have numerically for the diffusion for the concentration diffusion, we cannot bound our domain. We have
the simulation that you show at the end was not steady state. It was not.
No. We do this.
Stop the simulation.
Okay, we stop the simulation because we want just to see the evolution of the size repartition function. But of course, what I say here, we investigate the long-term asymptotic behavior in the perspective. We want to see it, but it's very difficult to take into account the position of particle and monomer and to look the long-term asymptotic behavior. We try it, but it's very difficult because the monomer or the particle, it's difficult to say something about here. We need to use a more rigorous scheme like Renault or antidissipative one but in this state we cannot say something rigorous on it. Okay.
So thank you again.